So we'll be talking about the actual Jupyter notebook now. So I'm running this in Google Colab. And as you can see, first of all, I've downloaded or imported some dependencies like NumPy and pandas for basic data manipulation and for plotting. I've got matplotlib here and pyplot from there. So I've uploaded this data. These are the first few rows of the data. That's all I can show you. But as you can see, so this is the format of the data. You have the date column, and then you have revenue, and then you have all the predictive variables. So there's Google spend, meta spend, Google impressions, meta impressions, Google clicks, Google impressions, and then there's a seasonal component. So this data set that you're seeing here, it has actually been worked on already. So some sort of cleaning or some sort of seasonal factor extraction, as you can see here. So seasonal decomposition. So some actions have already been taken on it. Largely clean data set. This is how the revenue looks like, as you can see. It started from zero here. This is the earliest data point. That's why. But otherwise, it nicely went up and then went down a little bit and has been having a sort of an upward trend ever um, since around May of 2025, or probably a little bit later than that. There was a dip in between, but yeah. So this is how it looks like. Then we, just changed the week date data type to date time. Basic manipulation stuff. This is how the columns will look like. As you can see, like I was just saying, for week date, the minimum date was, it was in November, 12th of November 2023, and the maximum date is 9th of March 2025. And these are all the spend. So the average spend here is around 29,000. So this is weekly data, remember. So it's around, say, 4,000, I'd say, on a daily basis. And for Meta, it's around 23,000, right? Weekly basis. There are, weeks where the spend has been pretty low. Let's look at revenue also. Obviously, we are talking about so this is 10 to the power 5. So that's the mean, and the minimum has gone down almost to 2.24, and the max is also pretty much on the higher side. So yeah, this is how the overall data set looks like, and you'll see that it's there's no non-balance, like I said, basically it's already been done. This is weekly aggregated data, and there's no non-value here. I'm sorry, there's no non-value here, and that's pretty much. So now we are talking about something, so what we have done here basically is just created an original revenue column because we are actually going to change the revenue column here. So this is going to be a thought experiment in a sense, because our objective here is to try and understand the impact of a particular campaign. So there's no real campaign here. That is something that I will probably show in later sort of sessions maybe, but it's for you to also come up with the idea. What I'm going to show here is something that you can apply. So the what I'm trying to show here is if there is an intervention, and if we know, suppose we know, so that's the the suppose part, uh, that the revenue is increasing by a certain percentage. Okay, that is something that's observed. But you want to also know that if it's the result of an intervention, you know two things. First of all, you have observed the data that there's an increase in revenue by a certain percentage, a mean increase over a certain period of time, and you also know that there was an intervention, a marketing campaign, for instance, at certain periods. So you want to know whether, first of all, it was positively impacting that, and if so, to what extent. So there's no real marketing campaign in this example, but it's something that we can, it's on a real data set. But so what this will do is, first of all, establish whether or not this is even correct. Okay, I mean, this approach is even acceptable to measure cause and impact. So that's what we're going to see whether or not. And we'll see at the end of the, since I'm spending so much time on it, obviously you understand it has worked. So the objective of doing this, as you understand, to create this duplicate column is because we're going to manipulate the revenue column. And this is the manipulation. So this is the intervention that I was talking about. The intervention, as you can see, is where you've taken a certain date range, and beyond this date range, we are just multiplying it by 40, by 1.45, meaning that there's a 45% increase of, in the post period. This is again observed, remember. So this is synthetically being input into the data, because this is obviously not going to be like, there's hardly going to be a case where it's going to be consistently 45%, right? So you understand that this is synthetically being introduced, but it makes sense because it's a good test of whether or not causal impact can now be actually calculated by the model. So the model has to retrieve this data. The model has to understand how much it has increased, okay, due to an intervention. So so after making this change, the revenue has been given that artificial synthetic bump of 45%. And after that, we plot it again. And if you compare it with the previous one, this was up to around 1.2 here, right? And now you see the pattern, the distribution remains exactly the same. It's just that it has got a bump now. Everything from that point onwards, I think the point was, let's see, the intervention date is 18/8, right? So 18th August 2024. So around this point, that's where it got the bump. Okay. And in fact, what I've done is gone ahead and plotted that as well. So this is a nice little plot where we are comparing the original and the post intervention, and then we are just trying to see what is going on. This is called an XV line, and an XV line is just nothing but shows the point of intervention. As you can see, 18/8/2024, and this is what is called the counterfactual. This is where it could have gone anyway. Okay. And again, obviously, this is where we have the luxury of knowing this because we are synthetically introducing into the data, right? In reality, we are not going to get this luxury of knowing the counterfactual. This is what the model has to learn, right? In this case, we know it. Now we're going to check if the model can learn it properly or not. So this is what has been observed. Remember, this green line here. This is the post intervention, and this intervention had occurred anyway. So in a real life situation, it will simply be the blue, and then you will have the green section. This dotted section won't be there, but this is something the model will learn, that if this intervention here at this point would not have occurred, then it would have gone this path, gone along the dotted line path. That's the counterfactual, and then it's going to calculate this difference, which is going to be the causal impact. And then, so we can see, I mean, the whole process is relatively very simple. There's not too much complicated math going on, but there is actually in the back end. That's why in the front end you see that it's so smooth and nice and uh, so easy to understand. But the thought experiment is very important. The thought process here, how this is being used. So now we install the PyCausalImpact package, and from CausalImpact we install or import the CausalImpact again. We do some basic manipulation and then check which are the weak entries that are present here. I'll tell you why this was done. Again, this is very basic data handling stuff, but even though it's basic, it's actually important to do that. Since it's weekly data, you have to decide a pre-intervention and a post-intervention period. Let's actually look at the next piece of code and understand better why we had to do that. So you have to come up with a pre-period which starts much earlier than the intervention and just ends just before the intervention date. Now, what I've initially done is I've given a date which was just 1 day prior. Like I had forgotten that it's actually a weekly data. It just kept my mind for a moment. And since it's 18/8, remember the intervention date here, I've given 17/8. Now it's through an error, right? Because it's not in the data set. So the date that you give, all the dates that you have to mention explicitly, they must be present in the data set, right? Since it's weekly data, so the most recent data, which is also prior to the intervention date, could only have been 11/8, right? So that's what I've done. That's the end date of the pre-intervention period, because that's the previous week. And then I started the post period. I started precisely from the week of the intervention. So in this case, as you understand, the intervention is not a singular temporal point, data point. It's actually a weekly temporal data point because we have the week date, the date column varying on a weekly basis. So it starts from that intervention week, and then it goes on to the last date of the date range entire data. So one point to note here is that remember what I just said, that this model is going to learn from the pre-intervention period and then apply that knowledge of this relationships between the input and the covariate and the outcome variable and try to understand the counterfactual. And then it goes on to calculate the difference and the causal impact from there. So that learning has to, in order for that learning to be comprehensive, it needs that, that sort of cushion, right? It needs a significant period to do the learning well. And therefore, the pre-learning period or the pre-period, that should be decent enough. And I have seen opinions like from experts that it could, should be several times probably than the post period, because this is kind of like test train split. Sorry, this is a tongue twister there. So the train test split that is often taken as 80-20%, something of that sort, right? So it's 4 times the training. So it's kind of like that in a sense. So yeah, that's something to bear in mind as well. Accordingly, the split should be done. So yeah, I mean, again, this is not exactly a split, but yeah, you get my point. So, yeah, so then we actually invoke the causal impact here, and then therefore this becomes an object, the causal impact package, and we simply pass these arguments here, the data frame, and pre and post periods. And then it sort of starts doing its little magic here. It actually calculates a lot of stuff. It gives you the actual prediction, 95% confidence interval, and then it gives the average, the cumulative, and gives absolute values and relative values. So what you really should be looking at is relative values. And for relative values, you see it has come up with 47%. And within a 95% confidence interval, the range is 47 to 48, which is very good, very, very decent range. So remember what our actual was? Our actual was 45%. Right? We gave a 45% synthetic push to the revenue, right? And then we wanted to check if the model has been able to pick it up. It has retrieved it pretty well, right? 47% is very, very close. 47.68%, 68 is pretty good. And then it does something more. It uses almost an LLM type nice summary report, right? It sums up the entire thing that has happened. So the above results are given absolute numbers and relative terms. Response rate will show and increase at 47.68%. And this is the interval for a 95%. This is the range with a 95% confidence interval. So this means that the positive effect observed during the intervention period is statistically significant and unlikely to be due to random fluctuations. So we also have the statistical significance here, right? 0.00%. This is the posterior probability of a causal effect, right? So this means that the causal effect can be considered statistically significant. And it's also interesting that you can actually compare the absolute effect to the original goal of the underlying intervention, right? And therefore, it bears a substantive significance. The question of whether this increase also bears, substantive significance can only be answered by comparing the absolute effect to the original. So I think this is a very interesting sort of an output. As you can see, these are the only few lines of code that are actually core causal impact. The rest was just data manipulation and just getting it ready. But that's pretty much it. And there are some assumptions here. We already talked about a few assumptions. We can take a look at it here. We'll pause the video. I'm not walking through each of those, but yeah, you probably understand what's really going on. So yeah, this is this is where the model can actually falter if the assumptions are not being made. But I think we have pretty much discussed the most important ones. And this is the plotting, by the way. So it's very nice. This is the actual versus predicted, and this is the difference. So you'll see that this lies somewhere between these two. That's why, that's the reason why, it's kind of like in between these two. And that's because it's the difference of these two. And then it's the cumulative effect. Okay. Again, very nicely presented. This gives you the counterfactual and the causal impact. So this is where we actually try to find out the inferences per column. This is all that is present, and this is what you can use under the impact here. And then basically what I'm trying to plot is called the residual. So we are just trying to understand how do they fare in terms of diagnostics. We have to have some sort of evaluative criteria, right? And you see that these are very common plots here that we get from the stats models. Okay, so we see from stats models with graphics, we can actually have these plots. So these are called the standardized residual plots. Okay, so residuals are nothing but the difference between the actuals and the predicted. And the standardized residuals over time, this is supposed to be very, sort of random. There should not be any trends here. So that's one of the things that should be the case here. But you see that there is actually a trend here for there's a definitive pattern here, and that's probably because it's not been able to pick up the change entirely, right? So we do have some variation here that's not been explained properly. We also have a histogram, uh, and what's really ideal is to have a normal distribution in this scenario, but we don't have one, right? So again, there is some element of uncertainty in the model, and again, this depends on the data set, right? So every data set is different, and after applying this model, because it's been trying to learn the past to understand the future, remember? So this is it's been trying to do. So this is what it thought the future is going to look like, and this is what was in the past, right? So yeah. So naturally, there's a difference in pattern. There's a difference in the nature of the data, and yeah, that's why the outcome has some sort of uncertainty built in. And see, even with the normal QQ plot, so all these lines here, they are supposed to be pretty much on the red line, but they're somewhat deviated here, and that means there's some sort of skewness. And you also have the ACF plot. You would ideally want all of these little bars here to be within the shaded region. That would show that the data is also stationary, but there's probably some sort of autocorrelation going on here because it's kind of gradual, right? It's not really, not everything is in the shaded region, and most importantly, it's not dropping off to zero. So ACF plot or a parallelogram, they have to sort of really, uh, become zero very fast if it's a stationary data set. So there's an element of non-stationarity in the data set as well. So there are some techniques to deal with that. I've talked about that separately, but this is the whole thing. This is, the diagnostics don't look super good here, even though the prediction was pretty much on mark. But the fact that the diagnostics look, it appears that there's room for improvement. That actually shows that, if it's given some sort of different data, uh, the output might not be very good. The model might not be able to predict it very strongly. So there are some ways to actually customize the model also, and you might be very interested in actually taking a look at some of those things. This itself is a customization. The basic implementation didn't contain this, but towards the end of this documentation here, you see there are sections like adjusting the model, so you can actually talk about, you can provide some special model arguments like number of seasons. So this is the custom seasonality that can be sort of weaved into the model. And then there are other options like number of instance samples, number of burn-in samples, standardization, priors, incidents we just saw, season duration, and then dynamic regression. So these are things that you can do. There's also custom modeling, and yeah, lots of stuff. And then there's Bayesian inference, and then yeah. So these are some important FAQs here that you can also take a look at. Changing font size. This is the validation part that I was just showing you, and then you can also take a look at the components of the output and also which predictor variables we use. So a lot of stuff that you can actually that you can check, and I think this has got a lot of potential. But yeah, some of those assumptions they really have to be met for you to be able to do this. So the whole crux of this analysis of this discussion was to just show you a single method of trying to establish cause and effect. Establishing causality is very hard. Let's just face it. It's not going to be a simple walk in the park. It's not going to be like, you just pick up something and you do it and then it's okay. Yeah, 100%. Not really. It's never really going to be 100%. It's going to be always hard. There's always going to be things you can question, but you start getting closer to the truth by leveraging these techniques. So causal impact by Google, this package is one such example. Then there are others like there are some solutions from EconML. Then there are some of these are by Uber, some are by some other companies. A lot of companies that come up with their own sort of statistical or advanced ML sort of methods for causal measurement. And EconML is one, DoY is one, PyY. So there are quite a few like these that you can actually take a look at them. You can just Google them up and you can find some of them. So you can have like EconML, Causal, just do that sort of such and see this Causal Force, DML. So yeah, there are so many options like this. I'll encourage you to go through many of these and see which one suits your exact requirements better. And yeah, that's pretty much it. I hope that this was useful to you. I'll be talking more and more about causality and causal inference and its impact in marketing measurement and how it can actually improve our perspective of what's working and what's not. So yeah, thanks for watching. If you have any questions, do let me know, and I'll see you in the next one.